Now that you know what is a type of input for the networks that we are going to look at, which uses the Hebb's learning, and what is a linear associator, in this video we are going to learn about the one of the simplest and most beautiful learning rules in neural networks, which is the Hebb's rule. And this rule, as we talked about earlier, comes from brain science, and it tries to answer a very simple question, which is how do neurons learn to associate one thing with another? And that is, if they are associated, then the associations become stronger. If they are not, then they get weaker. So uh, and we'll start out with uh, talking about patterns. So as we looked at earlier, patterns for in this case are going to be simple on off signals. So let's say 1 0 1 1 0. So this 1 indicates on, 0 indicates off. And if we have a bipolar signal, it could be -1 1 -1 1 and so on. So this would be off and this would be on. The +1 would be on. And each pattern here presents a state or idea. It could be a picture, a word, a command, a sensor reading. So the goal of associative memory is simple. When it sees a pattern P, it should output a pattern T. So we say that the input, as we drew earlier in previous videos, so the input is P and the output is A. But we have been saying that the output can also be written as T. So we'll use the T letter for the target. And linear associator, what it does is to store these input output pairs, we are going to use a very simple network that can be represented by A is equal to WP that we looked at earlier, where this is the input vector and this is the weight matrix and this is the output. So this multiplication, that is the heart of the Hebb's rule. And how does the uh, how does the Hebb's rule work? So it says that if an input neuron and an output neuron are on at the same time, then strengthen the connections between them. And mathematically, we can show that as follows: new W, or the updated weight matrix, is equal to old weight matrix plus the outer product of the target with the input. So what this means is we take the target vector, we take the input vector, and we perform an outer product of this. What it does is it creates a matrix that is of the same shape as the W matrix, and then we add it with the weight matrix to get us the new W matrix. So this outer product, it's like a rectangular stamp or a memory trace that gets written in W. So imagine the analogy of transparent sheets, and so each time we perform this outer product, we are sort of placing some sort of a pattern in our weight matrix that later we can later recall to get the target output for a corresponding input. And so to store many input output pairs, we just keep adding these sequences. And so what we can write, the way we can write that is as follows. We can say that W is equal to summation of q, lowercase q, is equal to 1 to uppercase q, pq pq transpose. And here note that if we try and expand this, it would essentially mean T1 P1 transpose plus T2 P2 transpose plus all the way up to T lowercase q, sorry, uppercase q, P uppercase q transpose. And so with this, we can also then uh, understand that uh, these P in the TQ and PQ transpose, they are vectors, and so those could be something like this: T1 T2 all the way up to TQ, and our input would be P1 transpose P2 transpose all the way up to PQ transpose. And that's the TP transpose that we have, where we are saying that this part right here is the T and this part right here is the part P that we have the transpose up there. So when W becomes a stack of such memories that we have taught the network, each of these PQ TQ pairs, it sort of leaves its own fingerprint in the weight matrix W, and that fingerprint is what we are uh, that is going to help us get the target output for a new input. Now uh, suppose we want the neural network to recall a memory. So I'm going to use the word and write it here. So recall. So we want to recall the memory. uh, what we can do it, we can give it a test input. Let's say that test input is pk. So what we would do is, to get an output, we simply would dot that test input with the weight matrix w, and that will get us an output. How does that work? We can substitute the value for w in there. So we could say that sigma q is equal to 1 to uppercase q pq PQ transpose, and then we have the PK out there. We can rearrange this to get sigma Q is equal to 1 to uppercase Q PQ PQ transpose PK. And so this is sort of the most important idea of this chapter, that we need to understand, this part right here. What this is telling us is, if if the new vector that we have, the pk, if it is in the similar direction as the vector that was already used to create the weight matrix, that's already in the matrix, the fingerprint is already there, then the dot product of those two would be higher. So the dot product tells us how similar the test input is to each stored input. So if the two patterns are in same direction, the dot product, so if they are in same direction, dot product is big, right? If they are orthogonal to each other, then this particular dot product would be 0. And if they somewhat overlap, uh, then the dot product would be somewhere in between. So I'll draw just a square of that size there. So during recall, that is uh, that is when we do this dot product right here, the target matching our inputs gets a strong weight. So if they match, it gets a strong weight. If they are unrelated, they get no weight. And if they are partially related, then they get some weight, which has an added factor to it, which is the error. So let's look at this a little more. If we if all the stored inputs in that we use to create our weight matrix, the P1, P2, all the way up to PQ, if they are all orthogonal, then if we do this dot product PQ transpose PK, what would happen is we would get a value of 1 if the PK is in the same direction as the PQ. So if they are similar, uh, and so we would get a good exact match for the target output. If they are not, then we would get a 0. So uh, if we again go back in this equation above, A would be equal to if this and this output, this part right here, if that part right here, if that is equal to 1, then we simply get our output TK. And that's a perfect recall, no errors, no mistakes, no mixing. So orthogonality means that each memory is stored in its unique direction. Now, what happens if the inputs are not orthogonal? What I mean by that is if we have the PQ transpose PK, and if that is not equal to 0 for some Q not equal to K, then this means that multiple memories can partially activate at same time. What I mean is that the patterns can uh, m- match to not just one previous fingerprint, but maybe it could match partially to several fingerprints. And in those cases, what can happen is that uh, uh, we would get an output which would be an error. So if we look at this A again, A would be equal to WPK, but this time in addition to this TK, which is the target output that we hope to get, we would also get something called as error or interference, which we can write here as sigma q not equal to k TQ, right? That's what already exists in that matrix, and to that we add the dot product of PQ transpose PK. So this part right here is the error part or the interference part, and that sort of uh, uh, blurs the output. So this is why pattern encoding and normalization of the input vector when we are using the Hebb's rule matters a lot. Let's now look at some example that helps us understand this, and hopefully that will make uh, the context that we talked about very clear. So imagine we have input vectors. So this is example. First we'll look at orthogonal case. So if we have input vector P1 that has values 1, 0, 0, 0, and the associated target output is 1, 0. This is supervised learning. So we supervised learning, which means that we already know the ground truth target output uh, when we are training the model. So therefore we have the T's here. The next one is P2. P2 is let's say that is 0, 1, 0, 0, and the target output for that input T2 is equal to 0, 1. Now because these are orthogonal, if we try and take a dot product of these two, so let's say if we say 1, 0, 0, 0 and dot that with 0, 1, 0, 0, that is simply going to be equal to 1 times 0 plus 0 times 1 plus 0 times 0 plus 0 times 0, and so that equals 0. So this is P1 transpose dotted with P2. And so that's sort of the confirmation that those inputs are orthogonal. If you now calculate the values uh, of T1 outer products of the target with the input, here is how we would do. This is our target 0 1 for T1, and then we transpose the input, which would then become 1 0 0 0. So this would become, we take this and multiply with sort of all of these, and so the output would be 1 0, or so let's do it the other way, 1 0 0 0. This would be just 0 0 0. So all of these zeros. And likewise, we can take the dot product or the outer product of, not dot product, the outer product of these two, T2 P2 transpose, where T2 is 0 1 and the P2 is 0 1 0 0. So we have four values there, and that would come out to 0. The top row would be all zeros, and the bottom row we have, this would be 0, this would be 1, this would be again 0 0. So we essentially multiply each element with everything in other, uh, and so to get our W, we simply are going to take these two and add them up. So W is simply going to be T1 P1 transpose plus T2 P2 transpose, and that will get us here. So I'm going to do the addition here. It's just the one there in the top row and just the one here in the bottom row. So that's our W matrix that we get, and we are now going, we can now test this particular W matrix if it helps us extract or get the target output, and if we run into any errors. And to do that, what we can do is just take our same P1. So if I take the P1 and dot that with this weight matrix right here, let's see what we get. So this is 1 0 0 0. This is 0 1 0 0, and our P is P with the column vector P is 1 triple 0. So 1 0 0 0. So if we perform this dot product, we get the only one in the top case because the rest three are zeros, and in the second we multiply this. So 0 times 1 is 0, 1 times 0 is 0. So this stays as 0, and that is equal to the T1. Awesome. So as you can see clearly, if the input vectors are orthogonal, the output that we get, in this case we used P1 and we didn't use some other new vector, just to show the point that if we have a test vector that is uh, aligned with whatever vectors have been in the weight matrix, then we get an exact match the uh, if the inputs are orthogonal. Now we can change this a little bit and make these inputs not orthogonal. So I'm going to scroll down here and say we now have a vector p1 that is 1 1 0 0 0. So that's the input, which is the same as before. So I could do a transpose there, or let's keep things the same as we did before. Rather than writing it horizontally, I'll just write it as a column as we did, and then the T1 for this is the same 1 0. Now the P2 has changed, so the P2, let's say it's 1 1 0 0, and the corresponding T2 is 0 1. If we now try and get the um, dot product of P1 transpose P2, you'll see that it is not going to be equal to 0. So that's our P1 transpose, and this is our P2. So here what we would get is 1 times 1 plus 0 times 1 um, plus 0 times 0. So 0 times 1 times 1 plus 0 times 1 plus 0 times 0 plus another 0 times 0. That gets us a value of 1. So this definitely is not, uh, these two are not orthogonal to each other. That is, they are not at 90 degrees to each other. And with knowing that, we are going to get an error when we try and compute the target later on from the weight matrix. We let's go ahead and first calculate the weight matrix. So for weight matrix, as we know, we need the following: T1 P1 transpose, outer product of that. We need the T2 P2 transpose, the outer product of that. So the first one, the outer product is going to be T1 is 1 0, and uh, the P1 transpose, that matrix, the column vector, sorry, we can simply write it as 1 triple 0. And then for T2 we have the column vectors as 0 1, and this is 1 1 0 0. If we perform the outer products, here we get 1 0 0 0, and this is going to be all zeros at the bottom. And the second case, we have all zeros in the top row and two ones in the bottom row. If I go ahead and add these, we would get 1 in the top row, rest would be 3 zeros, and then 2 ones in the bottom row with others as well. So that's our W. That is the W. That is the sort of the stored memory, if you say, where the fingerprints exist. That is the layered um, uh, transparent sheets of plastic on which we have fingerprinted P1 and P2 patterns or prototype vectors. And now if we go in there and say, hey, can I have a vector P1, assuming we know that we have already used it, but let's say that's a new vector, and say, can you find the target output for that? And say, hey, yes, we can. Let me just dot that P1 with the weight matrix that I just calculated, and that will get me the target output. So here is how I would do it. I take the weight matrix that we just calculated above and dot that with the input vector P1, which is just 1 followed by 3 zeros. And let's see what happens. So here we have 1, then plus 0 plus 0 plus 0, and then down here we have 1 plus 0 plus 0 plus 0. So what we get is 1 1. Well, that is not the same as T1, which is 1 0. So it is not the same. That's the whole point. So this is not equal to 1 0, right? So that was the original T1 that we knew, and we were hoping to get that target output when we used the P1 as input. But because the input vectors that were used to create this weight matrix P1 and P2, they were not orthogonal. That's why the weights that we have here in the weight matrix, they are probably not optimal, and therefore the output that we get has some errors in it, or we get this extra value that was supposed to be 0, but it's there because maybe that component that we see there is coming from the vector input vector P2. That's it. So that's sort of the overlaps of non-orthogonal inputs that could be thought of as errors. So that's all I wanted to talk about here, to give you a intuition about how Hebb's rule works. So even with four-dimensional input patterns, uh, the rule would remain the same. So if we stored the inputs, if the stored inputs that we have were all orthogonal, then the recall is perfect. If so, let's write down. If we have the stored inputs that are orthogonal, then the recall is perfect. So this is sort of the win-win situation. However, if they overlap somehow, then the output that we get uh, would have some information overlap uh, in the output, and so we may not get the exact output that we expected. There will be some errors associated with it. So that's the essence of how the Hebbian associative memory works, and I hope you now have uh, some intuition about how the linear associator works, how the Hebb's rule can be used to update the weight matrix, and how the orthogonality of input patterns is a big thing to get a output that is error free. If you have any comments or suggestions, please do let me know in the comments section below. I hope to see you all in the next video as well. Thank you.